3,000 miles below your feet. A solid iron sphere the size of the moon has stopped spinning the way it did your whole life. It is now turning backward. And it is just one signal. You will see a continent splitting apart, a magnetic shield cracking open, a fault slicing 2.5 meters in a single second, and a supervolcano breathing through a lid of molten rock. If something this strange grabs you, hit subscribe. There's much more coming. Hold on, we're going underground. Friday prayers were still ringing through Mandalay when the ground tore itself in half. It was March 28th, 2025. A cheap roadside security camera in central Myanmar was pointed at an empty stretch of dirt road. Nothing was happening. Then, in less time than it takes to blink, the road split. One side of the fault leapt sideways. The other side leapt the opposite way. 2.5 meters of solid earth shifted in 1 3/10 of a second. For the first time in the history of seismology, a major fault rupture had been filmed live. The earthquake was a magnitude 7.7. It was the strongest quake to hit Myanmar in over a century. The damage stretched all the way into Thailand. More than 5,000 people were killed. Buildings folded, bridges snapped. But the part that stunned scientists wasn't the destruction. It was the footage. Geologists had spent decades arguing about how faults actually move. Some believed ruptures travel like a steady wave. Others said the energy moves like a sharp pulse, focused and violent. They built their theories from instruments placed miles away from the action. Indirect data. Educated guessing. Then a roadside camera in Myanmar settled the argument in less than 2 seconds. When researchers from Kyoto University analysed the footage frame by frame, they noticed something nobody expected. The ground didn't slide in a straight line. It curved. The fault traced a slight arc as it ripped, like a whip cracking in slow motion. Imagine pulling a brick off a table by yanking the tablecloth. Now imagine the brick takes a tiny curved path instead of a straight one as it goes. That curve, multiplied across hundreds of miles of crust, is the difference between buildings standing and buildings collapsing. The fault that did this is called the Cascadia fault. It runs almost the full length of Myanmar, like a giant zipper waiting to be pulled. 2 enormous slabs of Earth's crust slide past each other along that line, grinding millimetre by millimetre. For decades the strain builds. Then in a heartbeat it releases. Here is what should keep you awake. That kind of fault is not unique to Myanmar. It is the same type of fault that runs through California, through Turkey, through New Zealand, through Indonesia. Strike-slip faults. They live under cities holding tens of millions of people, and until last year, nobody on Earth had ever seen one rupture in real time. The Myanmar footage is now being studied in every major seismology lab in the world. Researchers are rebuilding their models from scratch. The pulse-like rupture theory turned out to be partly right. The curved motion theory turned out to be partly right. But the speed surprised everyone. 2.5 meters in 1 3/10 of a second. For comparison, that is faster than a sprinter accelerating off the starting line. The ground beneath that road moved quicker than a human body can run. And the Cascadia fault is one of dozens of faults like it around the planet. All loaded, all waiting, all building strain right now. The Myanmar quake was a warning written in the dirt. But this surface story is just the entrance. The real strangeness is happening much, much deeper. 3,000 miles down, something even bigger is shifting. 3,000 miles below your shoes, there is a solid ball of iron and nickel, almost the size of the moon. It is hotter than the surface of the sun. It is held in place by gravity, suspended inside a swirling ocean of liquid metal. And for as long as humans have measured it, that solid ball has been spinning slightly faster than the rest of the planet. Until around the year 2010. That is when something inside Earth quietly broke. A team of geophysicists at the University of Southern California, led by John Vidal, spent decades collecting seismic data from one specific spot on the planet, the South. Sandwich Islands near Antarctica. Earthquakes there happen in the same locations, again and again, sometimes producing nearly identical seismic waves. Scientists call these repeating earthquakes. They are like a drumbeat that keeps the same rhythm for 50 years. If something deep inside Earth changes, the drumbeat changes with it. The team pulled data going back to 1991. They added in seismic signals from old Soviet nuclear tests in the 1970s. They cross-checked everything against quakes recorded in Alaska, on the opposite side of the planet, where the seismic waves pop back out after passing through Earth's centre. What they found was unsettling. The inner core had slowed down. Not just a little. It had slowed so much that it started moving slower than the planet's surface. In other words, relative to the ground you walk on, the heart of the Earth had reversed direction. The first time this happened in modern history was around 1970. Then it reversed again. The pattern looks like an oscillation, a giant pendulum swinging through a cycle that takes roughly 70 years. And we are right in the middle of one of those swings. Picture a marble suspended inside a glass of swirling water. The marble used to spin a touch faster than the glass. Now it is dragging behind. The water itself, our liquid outer core, is what makes Earth's magnetic field. So when the marble starts moving differently, the magnetic field starts behaving differently. Compass readings shift. Satellite paths drift. The length of a day changes by tiny fractions of a second. The change is small, 1,000th of a second per day. So small it gets lost in the noise of ocean tides and atmospheric churn. You will not feel it, your watch will not register it. But the instruments do not lie. Vidal's team confirmed the slowdown in 2024, then went deeper in 2025 with a study published in Nature Geoscience. They expanded their dataset to over 200 earthquake pairs. The reversal is real. The cycle is real. The mechanism is still up for debate. The leading theory points to two forces. The molten outer core, churning and turbulent, drags on the solid sphere from one side. The mantle above, with its uneven density, tugs on it from another. The inner core gets caught between them, wobbling on a decades-long cycle. But here is the question nobody has answered yet. If the inner core is reversing, is it staying the same shape? Is that perfect iron sphere still perfect? Or is something else changing down there at the same time? The answer, found in the same earthquake waves, turned out to be the strangest part of the entire story. For as long as scientists have studied it, the inner core has been described as a solid sphere, iron and nickel, held tight by crushing pressure. Hard, smooth, unchanging. The kind of object you draw in a textbook with a single clean circle. That picture is wrong. In December 2024, John Vidal stood in front of a packed room at the American Geophysical Union meeting and dropped a bombshell. The inner core, he said, is not just rotating differently, it is also morphing. The surface of the metal sphere appears to be deforming on a human timescale, not over millions of years, within decades. Reread that sentence. The most dense, most pressurized object on the planet is changing shape while you are alive. How could anyone possibly know? The answer comes from a specific kind of seismic wave called pkik. When a powerful earthquake fires off in the South Sandwich Islands, certain waves travel down through the mantle, through the liquid outer core, all the way through the solid inner core and out the other side of the planet. Sensors in Alaska catch them. The waves arrive carrying microscopic information about every layer they crossed. Vidal's team noticed something strange. Some waveforms recorded in the 1990s matched up perfectly with waveforms from 2023, like two musical notes hitting the same pitch decades apart. That confirmed the inner core had returned to a previous orientation, supporting the rotation reversal. But other waveforms refused to match. Their amplitudes had changed. The shape of the wave had shifted. If the inner core was only rotating, the waves should still match when the orientation came back around. The fact that they did not match meant something else was happening. Something physical. Something at the surface of the sphere itself. The most likely explanation is that the boundary between the solid inner core and the liquid outer core is not a clean line. It is a fuzzy, malleable zone. The molten metal swirling around the sphere is so turbulent that it actually pushes and pulls on the solid surface. The inner core deforms in response. Tiny mountains rise. Tiny valleys form. The shape of the most extreme object on Earth is being sculpted by the liquid that surrounds it. Vidali described it as almost science fiction, a place with different timescales, different materials, and forces no human will ever directly witness. Think of it this way. Imagine a perfect ice ball spinning inside a pot of boiling water. The water is so violent that it slowly carves grooves into the ice. The ice changes shape. But you cannot see the ice. You cannot send a probe to it. The only way you know it is changing is by listening to the bubbles in the water and the echoes off the bottom of the pot. That is exactly what seismologists are doing. This discovery breaks decades of assumption. The inner core was supposed to be the most stable, most boring part of the planet. Instead, it is the most surprising. Its rotation cycles, its surface deforms, its boundary shifts, and every one of these motions feeds back into the magnetic field that protects every living thing on the surface. Because here is the thing. If the engine room of the planet is changing, the shield it generates must be changing too. And it is. The shield, our magnetic field, is starting to crack open in one specific spot. Above the South Atlantic, between Brazil and the coast of Africa, there is a hole in Earth's magnetic shield. It is invisible. You cannot see it from a plane. You cannot feel it on the ground, but satellites passing through it get fried. Onboard computers crash. Data streams glitch. Astronauts on the International Space Station have reported flashes of light in their vision when they cross it, caused by cosmic radiation hitting their retinas. This hole is called the South Atlantic Anomaly, and it is growing. The European Space Agency has been watching it for over a decade with 3 satellites called Swarm, launched in 2013. The satellites measure the planet's magnetic field with extreme precision. In 2025, after 11 years of continuous data, the team published their results in the journal Physics of the Earth and Planetary Interiors. The numbers are sobering. Between 2014 and 2025, the anomaly expanded by an area roughly half the size of continental Europe. 11 years, half of Europe, the minimum magnetic field strength inside the anomaly dropped from about 22,430 nanotesla to 22,094. A field that normally moves at a glacial pace decade by decade is now changing at a sprint. Worse, the weakening is accelerating. Since 2020, the rate has picked up sharply, especially in a region southwest of Africa. A second, separate weak spot has appeared near the 0-degree meridian and is deepening 3 times faster than the original. The anomaly is no longer one blob. It is splitting into a complex, lopsided structure with 2 centres of weakness pulling at each other. To understand what this means, you have to picture how the magnetic field works. Earth's field is generated by the molten iron in the outer core, swirling around the solid inner core. That motion creates electric currents. Those currents create magnetism. The magnetic field pushes outward through the entire planet and forms an invisible bubble around it called the magnetosphere. That bubble deflects solar wind, cosmic rays, and high-energy particles that would otherwise sterilize the planet. The South Atlantic anomaly is the spot where that bubble is thinnest. The shield is bent inward there, like a dent in a car door. Charged particles from the sun can punch through the dent and dip much closer to the surface than anywhere else on Earth. Why is the dent growing? Beneath the South Atlantic, in the molten outer core, magnetic field lines are doing something they normally do not do. Instead of coming up out of the core, some of them are diving back in. These reversed flux patches drift around the core surface. One of them is moving westward under Africa. Another is drifting eastward under the central Atlantic. The 2 are pulling closer together. When they meet, the field above could weaken even faster. Picture the planet's magnetic field as a giant umbrella. The fabric is starting to tear in one spot. As the tear grows, more rain gets through. In our case, the rain is high-energy radiation from space. Right now, the anomaly poses no danger to people on the ground. The atmosphere still does most of the work of blocking radiation. But for satellites, for GPS, for the astronauts overhead, the dent is a real and growing problem. And the same mystery deep in the core that is reshaping the inner sphere is the mystery driving the hole above us. The next signal of that change is happening at the top of the planet. The North Pole itself is on the move. There is a place on Earth where every compass needle points. We call it the magnetic North Pole. It is not the same as the geographic North Pole, the spinning axis at the top of the globe. The magnetic pole is a wandering target, and right now it is running. When the magnetic pole was first pinpointed in 1831, it was sitting peacefully in the Canadian Arctic. For most of the next century and a half, it drifted slowly, a few miles per year. Slow enough that map makers could update charts every few decades and stay accurate. Then in the late 1990s, something kicked it. The pole started accelerating. By the year 2000, it was moving at about 30 miles per year. By 2010, it had reached 55 kilometers per year, roughly 34 miles. Aviation authorities had to update their navigation systems on an emergency schedule. The World Magnetic Model, which is supposed to be revised every 5 years, had to be re-released early because reality had outrun the math. The pole was bolting, out of Canada, over the Arctic Ocean, straight towards Siberia. After 2015, the pace slowed a bit. Then in late 2023, a new geomagnetic jerk kicked it again. A jerk is a sudden change in how the magnetic field is accelerating. Imagine driving smoothly on a highway, then someone yanks the steering wheel. The car keeps going, but its trajectory bends. That is what the planet's magnetic field did in 2023. The result, captured in the 2025 State of the Geomagnetic Field Report, was startling. The pole continued its drift towards Siberia at a remarkable speed, while regions of strong magnetic field shifted in equally strange ways. The strong field zone over Canada has shrunk by roughly the area of India in just over a decade. The strong field zone over Siberia has grown by an area roughly the size of Greenland. The magnetic balance of the planet is tilting eastward. What is causing this? The answer is buried 2,000 miles below the surface, in the swirling liquid iron of the outer core. Currents of molten metal there are constantly rearranging. When a strong patch of magnetic flux drifts in one direction, the magnetic pole follows. The Canadian patch is weakening. The Siberian patch is strengthening. The pole is being tugged toward the stronger one like a paperclip pulled across a table by a moving magnet underneath. Why are the patches shifting now? That is the open question. Some researchers suspect the changes inside the inner core, the slowdown, the deformation, are nudging the outer core into new flow patterns. Others think it is just the natural turbulence of a deep planetary engine playing out on human timescales. What is certain is the impact on the surface. Compasses are being recalibrated worldwide. Smartphone navigation, which depends on the magnetic model, is being patched in the background. Airports near high latitudes have had to renumber their runways, which are labelled by their magnetic heading. Aircraft routes over the polar regions, especially those flying between Asia and North America, have been redrawn. A pole that used to drift like a turtle is now moving like a hare. And underneath all of this, 3,000 miles down, the engine driving every one of these changes is itself producing surprises that shouldn't be physically possible. Because down there, solid rock is somehow flowing. Around 1,800 miles below the surface, just above the boundary between Earth's mantle and its outer core, there is a layer that has puzzled scientists for over 50 years. It is called the D layer, pronounced D double prime. It is roughly 200 miles thick, and inside it, something happens that should not be possible. Solid rock flows like syrup. When seismologists first studied the D layer in the 1970s, they noticed that earthquake waves passing through it suddenly accelerated. They sped up sharply, as if the rock changed character at that depth. Waves travelling in one direction moved fast. Waves travelling in another direction moved slow. The rock was somehow directional. For decades, no one could explain it. In June 2025, a team led by Motohiko Murakami at ETH Zurich finally cracked it. They published their results in Communications, Earth and Environment. Using a sophisticated computer model, they figured out that the rock at that depth is made of a strange mineral called post-perovskite, which forms only under extreme pressure. The crystals of this mineral are not symmetric, they have a preferred direction. When all of them point the same way, seismic waves race through them. When they are scrambled, the waves slow down. That explained the speed difference, but it raised an even bigger question. What could possibly make crystals deep inside the planet line up like soldiers in formation? To answer it, the team built a laboratory experiment that recreated the conditions of the D layer. They subjected post-perovskite crystals to the immense pressure and brutal temperature of the deep mantle, and they watched. The crystals began to flow. Not melt, flow, like cold honey forced through a narrow gap. Under enormous pressure, solid rock at over 2,000 degrees Celsius started moving horizontally, dragging the crystals into alignment. Within days, the crystals had sorted themselves into the same orientation. Seismic waves then accelerated through them, exactly the way they do inside the real planet. The discovery confirmed something extraordinary. There is convection happening in solid rock, not in liquid magma, in solid rock, just above the molten outer core. It is the slowest river in existence, but it is a river. Imagine a glacier on a mountainside. From a distance, the ice looks frozen and still, but if you watch over years, you see it flow downhill. The ice is solid the whole time. It is just that under enough pressure and over enough time, even ice behaves like a fluid. The D layer is the same idea, but with rock instead of ice, 2,000 miles down instead of on a mountain. This flowing rock layer matters for one big reason. It sits right at the boundary between the mantle and the outer core. It is the place where heat escapes from the core into the rest of the planet. The faster the rock flows, the faster heat is pulled up. The faster heat is pulled up, the faster the outer core churns. The faster the outer core churns, the more violently the magnetic field can shift. The D layer is the gear that connects the engine to the wheels. And right now, that gear is moving in ways scientists are only just learning to track. But there is something even stranger happening just above the D layer, something that contradicts everything textbooks once said about how earthquakes work. Pick up a geology textbook from 20 years ago, find the section on earthquakes. It will tell you that almost every quake on Earth happens in the crust, the thin outer skin of the planet, somewhere between 6 and 18 miles deep. The mantle below, hot and ductile, was supposed to be too soft to crack. The mantle could flow, it could not snap. That is what the textbook said. In February 2026, a team at Stanford led by graduate student Axel Wang published a paper in Science that quietly demolished that idea. They produced the first global map of a kind of earthquake that should not exist. Continental mantle earthquakes. Quakes that rip open the rock not in the crust, not at subduction zones, but inside the mantle itself, sometimes 50 miles below the surface, far from any plate boundary. For decades, scientists had argued whether such quakes were even real. A few suspicious tremors had shown up in seismic records. Skeptics dismissed them as misreadings. Believers suspected something deeper was going on. The data were too sparse to settle the fight. Wang and his advisor Simon Klemperer found a way to break the stalemate. They developed a method that uses tiny differences in seismic wave behavior to distinguish a true mantle quake from a crust quake. Then they applied it to global earthquake records. They found hundreds of them, all over the planet. The hotspots clustered in surprising places, under the Himalayas where India is ploughing into Asia, under the Bering Strait between Russia and Alaska, scattered under continents where no plate boundary should be active. The mantle, it turns out, is not a silent layer. It is cracking. Quietly. Continuously. About 100 times less often than crustal quakes, but real. What does it mean? Wang's team thinks some of these quakes might be aftershocks. When a big quake hits the crust, its seismic waves travel down into the mantle and rattle weak spots there. Other mantle quakes might be caused by something more dramatic. As subducted slabs of old ocean crust sink down into the mantle, they cool unevenly. They warp, they shear. Sometimes a slab snaps. The crack releases energy. But there is a third possibility, and this is the one that should make you pause. Mantle convection itself, the slow circulation of hot rock, might be strong enough in places to generate earthquakes. If that is right, the planet's interior is more active than anyone realized. Quakes are not just a surface phenomenon. They are part of an interconnected system that runs all the way from the core boundary to the ground under your feet. Picture the planet as a layer cake. We have always assumed only the top layer cracked. Now we are seeing fractures in the middle layer too. And those middle layer fractures might be coupled to the top layer ones in ways we are only beginning to map. The implications are huge for earthquake science. If mantle quakes can trigger or be triggered by crustal quakes, then long-term hazard models need to be rewritten. The seismic clock for major faults may be ticking on a deeper schedule than we knew, Wang put it plainly. The crust and the mantle, he said, might be part of a single interconnected earthquake cycle, layers of the world working as one system. And that system has more buried surprises in it. Buried tectonic plates that should have disappeared millions of years ago. Plates that, according to new evidence, are still warping the planet from below. Tectonic plates are not supposed to last forever. When two plates collide, the heavier one slides under the lighter one. It plunges into the mantle. It sinks. Over tens of millions of years, the cold slab is supposed to dissolve into the hot rock around it, lose its identity, and disappear. That is the textbook version. Reality, as scientists discovered in April 2026, is much weirder. A team published a study in Science Daily that mapped the deepest mantle in unprecedented detail. They used what they described as the largest collection of earthquake seismic data ever assembled. By tracking how shear waves moved through the lowest layer of the mantle, almost 2,000 miles down, they could detect deformation, areas where the rock had been stretched, sheared, or twisted. What they found was a planet still haunted by its past. The deformation patterns lined up almost exactly with where ancient subducted slabs are believed to have sunk over the last 100 million years. Pieces of old Pacific crust, fragments of seafloor that vanished from the surface long before any human walked the earth. Their ghosts are still there, 3,000 kilometers down, still warping the rock around them. The lead author, a researcher named Wolf, explained it carefully. The team was not surprised that the slabs left a mark. Geodynamic computer simulations had predicted exactly that. What was surprising was the scale and the clarity. For the first time, the predictions could be tested against actual seismic data covering the entire planet. The ghost plates showed up in roughly 2/3 of the regions studied. Why would these slabs still be active down there? Two ideas are competing. The first is that the slabs carry a kind of fossil memory. When they were near the surface, intense forces aligned the crystals inside them in specific patterns. As they sank, they took those patterns with them. The crystals are still pointing the same way, even after millions of years. The second idea is more disturbing. As the slabs hit the boundary between the mantle and the molten outer core, they slow down, pile up, and get crushed. The intense deformation at that boundary is happening right now. The slabs are being violently sheared as they collide with the core boundary, like cars piling up at the end of a highway. Either way, the bottom of the mantle is not a quiet graveyard. It is a museum of catastrophe, with old plates still influencing how heat and rock move through the planet. This matters because the deepest mantle controls how heat escapes the core. Where the slabs pile up, heat flows differently. Where slabs sit, the magnetic field above behaves differently. Some scientists now suspect that the South Atlantic anomaly, the hole in our shield, might exist precisely because of an old slab graveyard right beneath it. Imagine sliding a tray of ice cubes onto the bottom of a hot pot. The pot keeps boiling, but the boiling is now uneven. Where the ice cubes sit, the heat rises slower. Where they are absent, the heat rises faster. The pot stops boiling smoothly. It boils in patches. That is what the bottom of Earth's mantle looks like. A patchwork of cold ghost plates and hot rising plumes fighting each other for billions of years. And one of those rising plumes is at this moment slicing a continent in half. Drive across northern Kenya into southern Ethiopia, and you cross a place where the planet is tearing itself apart. The Turkana Rift Zone runs about 300 miles through the desert. It is part of a much larger feature called the East African Rift System, which stretches over 2,000 miles from Ethiopia all the way down to Mozambique. Along this enormous scar, the African continent is splitting into two pieces. The smaller eastern piece, called the Somali Plate, is drifting away from the larger western piece, called the Nubian Plate. The pace is slow, about 4 to 7 millimeters per year, roughly the speed your fingernails grow. But in April 2026, a team led by Christian Rowan at Columbia University published a study in Nature Communications that changed how serious this is. They analysed high-quality seismic data from the Turkana region and discovered that the crust under it has thinned dramatically. Across most of Africa, continental crust is about 30 to 40 kilometres thick. Under Turkana, it has been stretched down to roughly 13 kilometres, about a third of normal. This is a phase geologists call necking. It is exactly what it sounds like. The crust gets pulled and pulled until it narrows down like the neck of a bottle. Once necking starts, the rest of the breakup tends to accelerate. The thinner the crust gets, the weaker it becomes. The weaker it becomes, the easier it stretches. Past a certain point, magma from below punches through, the surface cracks open, and a new ocean begins to form. The Turkana Rift is the first active continental rift on Earth that has been clearly caught in the necking phase. It is the same mechanical process that created the Red Sea millions of years ago. It is the same process that, hundreds of millions of years before that, opened the Atlantic Ocean. And it is happening right now, slow enough to be invisible day to day, fast enough to be measured every year. The driver is a pulsing column of hot rock rising from deep in the mantle, beneath the Afar region of Ethiopia. Researchers at the University of Southampton, led by Emma Watts, mapped this column in 2025. They found something extraordinary. The plume is not just steady upwelling, it pulses, rhythmically, like a heart. Each pulse delivers a fresh batch of hot mantle material to the base of the African crust. The crust thins a little more. The rift widens a little more. Then the next pulse arrives. Picture pulling a stick of warm taffy. Slowly, steadily, with a tiny extra tug every few seconds. The taffy stretches, narrows, pinches, and finally splits. That is the African crust, in geological slow motion. Already the surface tells the story. In 2005, a 35-mile fissure opened in the Afar Desert in days, after a swarm of earthquakes and a massive injection of magma. In 2018, heavy rains in Myanmar, Kenya, exposed a gaping crack across a road. Volcanoes along the rift, like Mount Nyiragongo, Erta Ale, and Old Doinyo Lengai, erupt regularly. In 2025, a volcano named Haley Gubby erupted for the first time in recorded history. Eventually, geologists say, the Indian Ocean will pour into the Rift Valley. Landlocked countries like Uganda and Rwanda could one day have a coastline. A new ocean basin will be born. This will take millions of years. But the mantle plume that drives it is doing something right now that no one expected. It is breathing. The Afar Triangle in northeastern Ethiopia is one of the most hostile places on the planet. Summer temperatures climb above 120 degrees Fahrenheit. Salt flats stretch to the horizon, active volcanoes glow at night like wounds. 3 tectonic plates meet there in a triple junction, and below the surface, something unprecedented is happening. In June 2025, a team from the University of Southampton, working in the Afar region, published findings in Nature Geoscience that startled the geology community. They had detected a clear, repeating signal coming from deep in the mantle. A pulse. A geological heartbeat. The team, led by Emma Watts, used a technique called isotope geochemistry. They analysed lava samples and gases from across the Afar region. Different parts of the mantle leave different chemical signatures, like fingerprints. By comparing dozens of samples, the researchers could trace the path the molten rock had taken upward. What emerged was not the picture geologists expected. Most models had assumed that the plume rising under Afar was a steady, continuous column of hot material, like a slow pillar of smoke. The new data showed something different. The plume was channeled. It split into separate streams as it rose. Each stream carried slightly different chemistry. And each stream pulsed. The pulses arrive in waves. A burst of hot material rises. Then a quieter period. Then another burst. The rhythm is not perfectly regular, but it is unmistakable. Lead author Watts described the pattern as akin to a heartbeat, with each pulse pumping fresh, hot mantle material toward the base of the African crust. Why does this matter so much? Because each pulse weakens the crust above it. When a hot pulse arrives, the rock beneath the surface heats up, expands slightly, and becomes easier to stretch. The continental crust, already thinning under the East African rift, gets a little weaker every time the heartbeat fires. Over millions of years, those individual pulses add up to a continent splitting open. Think of it like rocking a heavy door off its hinges. You cannot pull it free in one yank. But if you push and pull rhythmically, again and again, eventually the screws give. Each push by itself does almost nothing. The pattern is what does the work. The Afar plume has been doing this for tens of millions of years. The pulses now reaching the surface are the latest in a long sequence. And they are not just opening the rift, they are feeding the volcanoes that mark its course. Eta Ale, with its rare permanent lava lake. Dalafia. Old Doinyo Lengai, the Mountain of God, which erupts a strange black lava that turns white when it cools. Each of these volcanoes is a chimney drawing on the same deep heartbeat. There is one more wrinkle. The Southampton team found that the chemistry of the pulses is not uniform. Some parts of the plume look ancient, fingerprints from the original early mantle. Others look more recent, like material recycled from old subducted ocean crust. The plume is a layered thing. It is bringing up bits of Earth's history with every pulse. That means the breakup of Africa is being driven by material older than the dinosaurs, mixed with debris of long-dead ocean floors. The continent is being torn apart by its own past, beat by beat. But Africa is not the only place where the planet is splitting in real time. On the other side of the world, off the coast of the United States, an entire subduction zone is dying. Off the coast of Oregon, Washington, and Northern California, a slab of ocean floor has been sliding under the North American continent for tens of millions of years. The fault where they meet is called Cascadia. It is famous for being capable of producing some of the largest earthquakes on Earth. A magnitude 9 quake hit it in 1700. Another one is expected, eventually. But in October 2025, scientists at Louisiana State University published a study showing that something even stranger is happening at Cascadia. The subduction zone itself is breaking apart. For the first time in history, researchers caught a subduction zone in the act of dying. Lead author Brandon Shuck and his team used a technique called seismic reflection imaging. Picture an ultrasound, the kind doctors use, but aimed at the seafloor. A research vessel sent powerful sound waves down through the water and into the crust. The echoes bounced back, and were captured by a 15-kilometre-long line of underwater sensors trailing behind the ship. Combine the echoes, and you build a three-dimensional picture of the rock layers below. What the picture revealed was unsettling. The oceanic plate that has been sliding under North America is not behaving like a single sheet anymore. It is fracturing, tearing into pieces, forming microplates. The breakup is happening progressively, fault by fault, like a sheet of glass cracking from one edge inward. Schuck described it as watching a train derail in slow motion, one car at a time, instead of all at once. This kind of breakup had been theorized for decades. Geologists had even found evidence of it in ancient rock records. Mysterious fragments of vanished plates would show up scattered across continents, with no clean explanation for how they got there. The Cascadia data finally show how. Subduction zones do not just shut off cleanly, they unravel. When a slab tears, gaps open in the descending plate. Geologists call these gaps slab windows. Through them, hot mantle material can rise toward the surface, creating bursts of new volcanism. Old volcanoes that should have gone quiet sometimes reignite. New ones can appear in unexpected places. The geologic record of the Pacific Northwest is full of these unexplained bursts. The slab window theory finally connects the dots. What does this mean for people living above Cascadia? In the short term, not much changes. The risk of a major earthquake along the main subduction zone is still real, but the new tiers do not appear to make it more imminent. The big Cascadia quake everyone has been preparing for is still expected to come from the main locked section of the fault, not from the breakup at the edges. In the long term, the picture is more profound. The Cascadia subduction zone, which has been a major engine of West Coast geology for 50 million years, is winding down. New microplates are being born. New plate boundaries are forming. The map of plate tectonics is being redrawn in real time, off the coast of Seattle. This is how continents change. Not in single dramatic events, but in slow episodic breakdowns spread over tens of millions of years. And while one subduction zone is dying, another part of North America is sleeping uneasily on a lid of molten rock. Yellowstone is not a mountain. It is the opposite of a mountain. It is a giant collapsed bowl, 55 miles across, called a caldera. It was formed by some of the largest volcanic eruptions in Earth's history. The most recent one, 640,000 years ago, blew enough rock and ash into the sky to bury most of North America in a thick layer of debris. The volcano did not die after that. It went to sleep. For a long time, scientists could not figure out exactly how the system worked. They knew there was magma down there. They knew it was huge. But the top of the magma reservoir, where pressure builds and gas accumulates, was a mystery. Estimates of its depth range from 3 to 8 kilometers, a massive uncertainty for a sleeping monster. In April 2025, that uncertainty got resolved. A team from Rice University, the University of New Mexico, the University of Utah, and the University of Texas at Dallas, led by Brandon Schmant and Chenglong Zhuan, published a study in Nature. They had used a 53,000-pound vibrating truck called a vibroseis truck, the kind oil companies use for exploration, parked on roadside turnouts inside the national park, working only at night to avoid disturbing visitors. The truck shook the ground hundreds of times. Each shake sent seismic waves into the crust below. Hundreds of seismometers scattered across the caldera caught the echoes. The result was the clearest image ever made of the top of Yellowstone's magma reservoir. It sits exactly 3.8 kilometers below the surface, about 2 1/3 miles down, and it has a sharp boundary, like a lid. The lid is not solid rock. It is a thin layer of partly molten material laced with bubbles of supercritical fluid, about 14% porous. Half of those pores are filled with gas, mostly water and carbon dioxide squeezed out of the magma below. The lid is sealing in pressure, but not perfectly. It leaks. Slowly. Steadily. Schmant likened the system to breathing. The supervolcano inhales as new magma rises and gas accumulates. Then it exhales, releasing some of that gas through cracks in the cap, up through the crust, and out into the geysers and hot springs and steam vents that make Yellowstone famous. Old Faithful is, in a sense, the volcano breathing out. This is good news. Eruptions tend to happen when the porosity at the top of a magma chamber climbs above a certain threshold. Too many bubbles, too much pressure, and the lid bursts. At 14% porosity, Yellowstone's lid is well below the eruption threshold, but pressure is being vented as fast as it builds. The system is in what scientists call a state of repose. In other words, Yellowstone is breathing comfortably in its sleep, but that does not mean the volcano is harmless. Underneath the cap sits a far larger magma chamber, and underneath that, going much deeper than anyone realised until recently, lies a second reservoir. A reservoir so large that the previous numbers for Yellowstone's plumbing have to be rewritten. That hidden lower reservoir is the part of the story most people have never heard. For decades, scientists believed they understood Yellowstone's magma system. There was an upper magma chamber, a few miles below the surface, holding partly molten rock. Beneath it, a hot mantle plume reached up from deep inside the planet. In between those two features, there was supposed to be empty rock, just a connecting pipe. In 2015, a study in the journal Science blew that picture apart. Updated and refined ever since, the discovery has only gotten stranger. A team at the University of Utah, led by seismologist Xin-Hua Huang and supported by Robert Smith and Jamie Farrell, combined two completely different sets of seismic data. Local quakes recorded by Utah's network, distant quakes recorded by a continent-wide array called EarthScope. Each network specialised in a different depth range. Together, they gave the first complete view of what lies under Yellowstone. What they found was a second, deeper magma reservoir. It sits between 12 and 28 miles below the surface. It is roughly 4.5 times larger than the upper chamber. To put that into a number people can feel, the lower reservoir contains enough hot, partly molten rock to fill the Grand Canyon 11 times over. The upper chamber, by comparison, would only fill the canyon about 2.5 times. This deeper reservoir had never been seen before. It changes everything about how scientists think about Yellowstone. Here is why. The upper magma chamber has been the immediate source of every supereruption Yellowstone has produced. When that chamber empties, the surface collapses into a caldera, but the chamber by itself only holds a finite amount of magma. After it erupts, it should be empty for a long time. Except now we know it is not. The lower reservoir is constantly feeding the upper chamber. New magma flows up from the deep system into the shallow one through a network of cracks called dikes and sills. The supervolcano has a refilling system. This also solved a long-standing mystery. Yellowstone has been emitting more carbon dioxide from its soil and geothermal vents than the upper chamber alone could explain. Where was the extra gas coming from? The answer, finally, was the lower reservoir. Gas was rising from the deeper, larger pool of molten rock and seeping all the way to the surface. The good news, repeated by every researcher involved, is that the discovery does not increase the danger. The annual chance of a supereruption at Yellowstone is still about 1 in 700,000. The system is the same as it has always been. We are simply seeing more of it now. Picture an iceberg. Ships used to think the visible tip was most of the ice. Then sonar showed them the much larger mass below the waterline. The iceberg did not change. The view did. Yellowstone is the geological version of that revelation. The lower reservoir is also not full of liquid magma. It is a sponge-like network of hot rock with pockets of melt scattered through it. The upper chamber is about 9% molten on average. The lower reservoir is only about 2%. Both are well below the threshold scientists associate with imminent eruption. Still, the size of the system is humbling. Most of Yellowstone is invisible. Most of the threat, if a threat ever returns, is hidden deep below the breathing cap. And while Yellowstone breathes peacefully, the planet has been producing the strongest earthquakes ever recorded. In late July 2025, just off the coast of Russia's Kamchatka Peninsula, the seafloor moved. The earthquake registered a magnitude of 8.8. According to the United States Geological Survey, it ranked among the 10 strongest earthquakes ever measured by modern instruments. Coming from the ocean floor in one of the most volcanically active regions on the planet, it shook a chain of islands across the North Pacific, sent tsunami warnings rippling all the way to Hawaii and Japan, and reminded the world how small humans actually are when the planet's plates start moving. To understand how rare a magnitude 8.8 is, consider the numbers. The USGS estimates that around 55 earthquakes happen every day, somewhere on Earth. That works out to roughly 20,000 per year. Most are too small to feel. About 15 per year reach the magnitude 7 range. Only about 1 per year reaches magnitude 8 or higher. A magnitude 8.8 is a once-a-decade event, sometimes once every 2 decades. The energy released in such a quake is hard to grasp. The Richter scale is logarithmic, which means each whole number is roughly 32 times more energetic than the one below it. A magnitude 8.8 is about 1,000 times more powerful than a magnitude 6.8. It is the difference between a stick of dynamite and an entire freight train of explosives. The Kamchatka quake came from a subduction zone. The Pacific plate is plunging under the Okhotsk plate at the western edge of the Pacific Ring of Fire. Strain has been building there for centuries. When it released, the seafloor lurched several meters in a single fault rupture that lasted roughly 1 minute. Tsunamis were generated immediately. Coastal regions along the peninsula evacuated. The neighbouring volcanic chain, already active, lit up with new tremors as the shaking nudged magma chambers nearby. What makes this quake especially interesting is that it was not the only one in 2025. Earlier in 2025, March brought the magnitude 7.7 Myanmar quake, the one captured live by a roadside camera. That was the strongest quake to hit Myanmar in over a century. December 2025 produced a magnitude 7.0 in Alaska. Earlier in 2024, a magnitude 7.5 hit the Noto Peninsula in Japan, causing extensive damage. In 2026, a global earthquake surge made headlines as multiple large events clustered in a short window. None of this proves that earthquakes are getting more frequent overall. Statistically, the long-term average has been steady for decades, but the recent cluster has been heavier than usual on the high end. More magnitude 7s, more magnitude 8s. Some seismologists are quietly asking whether something is shifting in the way strain releases globally. There is no scientific consensus on this yet. Earth's plate motions are slow and steady. The clusters could be coincidence, the natural noise of a planet that occasionally fires off big quakes in bunches. Or it could be a signal of deeper changes finally translating to the surface. The same deep changes happening in the inner core, magnetic field, and the mantle. What is certain is that 2025 was a year of severe shaking. Tens of thousands of buildings were damaged across continents. Thousands of people were killed. Economies took hits. The Federal Emergency Management Agency now estimates that earthquake damage costs the United States alone about $14.7 billion every year. And the next major rupture might come from the very same subduction zone we just saw in the act of unravelling. The dying subduction zone off the coast of the Pacific Northwest is not just falling apart, it is opening doors. When the Cascadia slab fractures into smaller microplates, gaps form between the pieces. Those gaps are called slab windows. They are the parts of the descending plate that have torn away, leaving a hole through which the hot mantle below can rise. Slab windows are not theoretical. They have been mapped in ancient rock records all over the world. What was new in 2025 was watching one open in real time. The Louisiana State University team, led by Brandon Shuck, identified at least one large tear in the Cascadia slab, with hints of more forming nearby. As each tear grows, mantle material flows up through the gap. That material is hot. It is buoyant. It can melt the overlying crust and produce new volcanic activity. Here is why this matters for the surface. Volcanoes in the Pacific Northwest, like Mount St. Helens, Mount Rainier, Mount Hood, and Mount Adams, are normally fed by magma generated above the still intact part of the descending slab. As the slab sinks, water trapped in its rocks gets squeezed out. The water lowers the melting point of the mantle above, creating magma. That magma rises and feeds the volcanoes, but where the slab has torn, the geometry changes. New magma sources appear. Existing volcanoes can receive heat from below in different ways. New, smaller volcanoes can pop up in places that were never volcanic before. Geologists looking at the rock record across the western United States have long noticed something puzzling. Volcanic activity in the region has not followed a steady pattern. There have been bursts, pauses, sudden shifts in where eruptions cluster. For decades, no model could explain why. Now, with the Cascadia data, the picture is clearer. Each burst probably corresponds to a slab tear. Each pause corresponds to a period when the slab was intact. Volcanic rocks' ages get younger or older in patterns that match the step-by-step tearing predicted by the Cascadia model. It is like a sequence of dominoes falling, but each domino represents 1 million years of geology and a fresh round of eruptions. What does this mean for people living in the Pacific Northwest? Researchers are clear that the discovery does not significantly change short-term hazard estimates. The big Cascadia subduction zone earthquake, the one that has been overdue for decades, is still the dominant threat. Its source is the still locked main section of the fault, not the breakup zones at the edges. But scientists are now investigating whether a major earthquake could rupture across one of the new tiers. If a quake were to jump from the locked section into a fragmenting microplate, the rupture pattern could be unusually complex. Energy might travel in unexpected directions. Computer models of seismic shaking, currently calibrated for a single clean rupture, would need to be updated. Researchers are also asking how the tiers might affect the way seismic waves travel. A fragmented slab is a different acoustic environment than a solid one. Shaking patterns at the surface could be more uneven, with some regions amplifying ground motion while others dampen it. The bottom line is that the Pacific Northwest sits over geology that is more complicated than anyone realized. Every new study peels back another layer. But the strangest thing about the deep mantle is not the slabs or the tiers. It is that solid rock down there can suddenly speed seismic waves up just by lining up its crystals. Drop a bell into a swimming pool, and the sound waves travel about 4 times faster through the water than they would through air. Different materials carry sound at different speeds. The same is true for seismic waves travelling through Earth. Most of the planet's interior carries seismic waves at fairly predictable speeds. Speeds that depend on temperature, pressure, and the kind of rock involved. But there are spots where the waves do something they should not do. They suddenly accelerate. They speed up sharply, then slow down again, with no obvious reason. The most famous of these spots is the D layer, the strange zone just above the core-mantle boundary. The waves there have been racing through one specific direction for as long as seismologists have been listening. Why? In June 2025, the team at ETH Zurich, led by Motohiko Murakami, published a study that finally cracked the puzzle. The acceleration was caused by crystals, not just any crystals. A mineral called post-perovskite, which only forms under the brutal conditions found near the core-mantle boundary. Pressures over 1 million times atmospheric. Temperatures over 2000 degrees Celsius. At those depths, ordinary mantle minerals collapse into a denser structure with a flat plate-like shape. The plates have a strong preferred direction. Sound moves quickly along the flat face of each plate and slowly across its edge. If all the plates inside a region are scrambled randomly, the average speed is normal. If all the plates line up and point the same way, sound rockets through them. Murakami's team built a laboratory experiment to test the idea. They squeezed post-perovskite samples between 2 diamonds, recreating the pressure of the core-mantle boundary, and they heated the samples with lasers to recreate the temperature. Then they watched the crystals over hours. They watched the crystals turn. Under shear, in other words under sideways force, the post-perovskite plates began rotating to align with the flow direction. Within hours, they were all pointing roughly the same way. Seismic waves shot through the aligned sample fastest in exactly the direction the model had predicted. This experiment proved two things at once. First, that the speed jumps in the D layer are caused by aligned crystals. Second, and this is the bigger discovery, that solid rock at the core-mantle boundary is actively flowing right now. The crystals would not align unless something was pushing them sideways. Something is. Solid-state convection is happening down there, slow and steady, dragging the crystals into formation. Picture a school of fish in a strong current. Each fish is solid. The fish are not melting into water, but the current pushes them all to face the same direction. To an observer, the fish look like a single organized stream. That is what is happening with post-perovskite crystals 2,000 miles below your feet. The implications run deep. The D layer is the hot, restless interface where the mantle meets the outer core. It is the gateway through which heat escapes from the core. If the rock there is flowing more vigorously in some places than others, it changes how heat reaches the surface. It changes how mantle plumes form. It even changes how the magnetic field is generated above. The crystals, in other words, are not just pretty geometry. They are the readouts of an engine. And right now, that engine is showing signs of running differently than it used to. Because Earth's interior, scientists are now realizing, is cooling faster than the textbooks predicted. Every planet has a thermal lifetime. It is born hot, formed in violent collisions that pack the interior with heat. Then, over billions of years, it slowly loses that heat to space. As the heat drains, the interior solidifies. Convection slows. Volcanoes go quiet. The magnetic field weakens and eventually dies. That is what happened to Mars. The red planet was once volcanically active, with a magnetic field and possibly oceans. Over a few billion years, its interior cooled. The convection in its core stopped. The magnetic field shut down. Solar winds stripped away most of the atmosphere. Today, Mars is a cold, dead world, with only a faint, frozen pulse of geological life. Earth has always been treated as the lucky exception. Our planet is bigger, hotter, slower to lose heat. Our magnetic field is strong. Our volcanoes still erupt. Our continents still drift. The textbook said we had billions of years left before our interior would significantly cool. In the last few years, that comfortable picture has cracked. A team studying the chemistry of Earth's deep interior, working with high-pressure laboratory experiments, found that the rate at which heat moves through the lower mantle is significantly higher than previously believed. The minerals down there conduct heat more efficiently, especially that strange post-perovskite with its aligned plate-like crystals. Aligned post-perovskite is a much better thermal conductor than the average rock. That means heat is escaping the core faster than the old models assumed. This discovery, supported by seismic observations and confirmed in computational simulations, suggests that Earth's interior is cooling several times faster than the textbook. Estimates. The numbers are still being argued. Some studies put the new rate at twice the old, others go higher. But the direction is clear. The planet is losing heat to space more quickly than anyone realized. What does that mean in practice? In the very long term, billions of years out, it means Earth could end up looking more like Mars sooner than expected. The convection in the core would slow, the magnetic field would fade, the volcanoes would die down. In the much shorter term, it might explain some of the strange behavior we are seeing now. A core that is cooling faster is a core that is changing faster. The inner core would solidify more rapidly, capturing more iron from the outer core. The outer core flow patterns would shift. The magnetic field, generated by those flow patterns, would respond. Reversed flux patches like those under Africa might be exactly the kind of disturbance we expect when a deeply churning system starts to lose heat in uneven ways. In other words, the planet might be running its long-term thermal program a bit faster than expected, and the surface effects might already be measurable. Picture a freshly poured cup of coffee. While it is hot, it steams off energy in steady, predictable swirls. As it cools, the swirls become more irregular. Eddies form and collapse. The surface gets choppy in unexpected places. That is what a cooling planet does too. The thermal patterns get more complex as the energy budget tightens. There is no need for alarm. The change is still on geological timescales. No one alive will see the magnetic field shut down or the volcanoes go silent. But the discovery does add another piece to the puzzle. Something is shifting beneath our feet. The inner core is reversing. The shape is changing. The rock is flowing. The shield is cracking. The continents are splitting. And now, the engine itself is running a little faster than it should. What comes next pushes even further out from anything textbooks ever described. Because beneath these surface signals, scientists are finding evidence that the rules of physics in the deep Earth might not be the rules we thought. Every once in a while, the Earth's magnetic field does something that should not be possible. It jerks. A geomagnetic jerk is a sudden, sharp change in how the magnetic field is accelerating. The field is always slowly drifting, always subtly bending. That is normal. But every few years, somewhere on the planet, the second derivative of the field, the rate at which the rate of change is changing, snaps to a new value, almost overnight in geological terms, within months in human ones. Think of it like driving a car. The position of the car is changing as you move. The speed is the rate of change. The acceleration is the rate of change of the speed. A geomagnetic jerk is the moment when someone suddenly stomps the gas pedal, even though the car keeps moving. The trajectory bends. The first one was identified in 1969. Since then, geophysicists have catalogued dozens of them. They tend to last only a year or two, but their fingerprints stay in the data for decades. The most recent confirmed jerk began in late 2023 and rolled into 2024. The 2025 State of the Geomagnetic Field Report flagged it as one of the major events of the year. After that jerk, the magnetic North Pole resumed its rapid drift towards Siberia. The South Atlantic anomaly accelerated its expansion. Strong field zones over Canada and Siberia continued their tug-of-war. Where do these jerks come from? The leading explanation involves waves travelling through the molten outer core. The outer core is not just a smooth bath of liquid iron, it is a turbulent ocean with currents, eddies and waves that can cross the entire core in months or years. Some of these waves, called magneto-Coriolis waves, can carry sudden bursts of magnetic energy from the deep interior up to the surface of the core. When such a wave hits the core-mantle boundary, the field above it snaps to a new pattern. Picture dropping a stone into a still pond. Most of the ripples are small, but every once in a while, a wave reaches the shore that is sharper and faster than the others. Geomagnetic jerks are the planet's version of those sharper waves after they have crossed 2,000 miles of liquid iron. Why does this matter? Because every device on Earth that depends on a magnetic reference, from compasses to airplane navigation systems to oil drilling rigs, uses a model of the field. The World Magnetic Model is updated every 5 years on a schedule based on the assumption that the field changes smoothly. A jerk breaks that assumption. After a jerk, the model is suddenly wrong. Aviation regulators, navigation companies, and military planners have to scramble to issue corrections. The jerk in 2023 was severe enough that it pushed deviations beyond the normal operating margins of high-latitude navigation. Pilots flying polar routes between Asia and North America had to use updated magnetic data sooner than the regular schedule allowed. Geomagnetic jerks are also a window into the planet's deep behaviour. By tracking how often they happen and where they originate on the core surface, geophysicists can map the wave patterns inside the outer core. The maps are not pretty. They show a core that has gotten more dynamic in recent years, with more frequent jerks and stronger ones. Some researchers suspect that the increasing jerk rate is connected to the slowdown of the inner core. As the inner core's rotation changed in the past 15 years, the coupling between the inner and outer cores would have shifted. New flow patterns would emerge, new waves would propagate, new jerks would arrive at the surface. The deep engine of the planet is running on a slightly different rhythm, and every couple of years now, it sends a sharp pulse outward to remind us. The pulses are getting more interesting, and one of them, drifting beneath the southern hemisphere, has scientists especially concerned. To understand the South Atlantic anomaly properly, you have to understand reversed flux patches. Earth's magnetic field is generated by currents in the outer core. Most of those currents produce field lines that exit the core in the southern hemisphere and re-enter it in the northern hemisphere. That is the dipole pattern, the shape that makes a compass needle behave the way it does. North seeks one direction, south seeks the other. But the dipole is not perfect. In some patches on the surface of the outer core, the field flips locally. Lines that should be exiting are diving back in. Lines that should be entering are coming out. These spots are called reversed flux patches. They are like dimples in a giant magnetic balloon. The dimples weaken the global field above them and strengthen it slightly nearby. In November 2025, the European Space Agency's swarm team, led by Chris Finlay at the Technical University of Denmark, published the most detailed map ever, made of these patches. 11 years of continuous data, every drift, every growth, every shift, captured. The map showed something unsettling. A large reversed flux patch under southern Africa was drifting westward. Another, under the central South Atlantic, was drifting eastward. The two were moving toward each other. Where they meet, the dimples in the magnetic balloon merge. The dimple gets deeper, the field above gets weaker. The South Atlantic anomaly, which sits directly above the converging patches, is being eroded by their motion. Finlay's team described the field beneath the anomaly as something nobody normally sees. In the southern hemisphere, magnetic field lines should be exiting the core. Instead, beneath the anomaly, lines are diving back in. The motion of one of these reversed regions westward over Africa is contributing directly to the weakening visible at the surface. This is happening right now, not in some long geological future. Year by year, decade by decade. Why are the patches moving? The leading idea is that they are being carried by flows in the outer core. Just as wind moves clouds across a sky, currents of liquid iron move magnetic field structures across the core surface. The patches drift with the underlying flow. The flow is influenced by the temperature differences between the inner core, the mantle, and the boundaries of the outer core. As any of those boundary conditions change, the flow changes and the patches drift to new locations. In recent decades, the flow patterns appear to have shifted, whether because of inner core rotation changes, faster mantle cooling, or some interaction between the two. The outer core is reorganizing. The reversed flux patches are the visible footprints of that reorganization. Imagine a slowly spinning bowl of soup with a few darker swirls floating in it. The swirls drift along the surface, sometimes merging, sometimes splitting. From above, you see those swirls as cool spots in the soup. The cool spots tell you something about how the soup itself is moving below. The reversed flux patches are Earth's version of those swirls. They are the readout of an enormous invisible flow. The current trajectory has scientists watching closely. If the patches continue to drift the way they are, the South Atlantic anomaly will keep growing for at least the next several decades. Some models predict the anomaly will eventually split into two distinct weak zones. Others predict a single, broader region of weakness. Either way, the field above the southern hemisphere is changing in a way unique in modern observation history. But the same engine producing that drift is also rearranging the strong parts of the field far to the north. While the South Atlantic anomaly grows, the northern hemisphere is hosting a different kind of magnetic struggle. Two strong field zones are pulling against each other across the top of the planet. One sits over Canada. One sits over Siberia. They are not friends. For most of recorded history, The Canadian zone was the dominant one. It anchored the magnetic North Pole. It kept compass needles pointing toward the Arctic archipelago. Its strength shaped magnetic readings across most of North America and Northern Europe. In the last 2 decades, that has changed. The SWARM satellite mission, in 11 years of measurements ending in 2025, found that the strong field region over Canada has shrunk by about 0.65% of Earth's surface area. That is roughly the area of India. The strong field region over Siberia, meanwhile, has grown by about 0.42% of the planet's surface. Roughly the area of Greenland. A magnetic India is missing from Canada. A magnetic Greenland is gaining over Siberia. The shift is responsible for the rapid drift of the magnetic North Pole. The pole follows the strongest local patch. As the Canadian patch weakens and the Siberian patch strengthens, the pole tracks towards Siberia. It is a kind of magnetic tug-of-war, with the pole as the rope. What is causing the imbalance? Once again, the answer is in the outer core. Currents of liquid iron beneath northern Canada have weakened and broken up. Currents beneath Siberia have organised into a tighter, stronger pattern. The change appears to have begun in the late 1990s and accelerated through the 2010s. Picture 2 hands rolling balls of dough on a table. For decades, the Canadian hand pressed harder, gathering the dough into a large mass. Then the Siberian hand started pressing harder. The dough began migrating across the table. The mass under the Canadian hand thinned. The mass under the Siberian hand grew. The centre of the dough, which is the pole, slid eastward. The implications are practical. Aircraft navigation systems are calibrated to magnetic headings. Runways at airports are numbered based on their magnetic compass orientation. As the field shifts, runways and routes have to be updated. Several airports near the magnetic pole, particularly in northern Canada, have already had their runway numbers changed in the last decade. More changes will come. There is also a subtler effect. Animals that navigate using magnetic fields, including migratory birds, sea turtles, salmon, and certain whales, encode magnetic landscapes into their behaviour. As the field shifts, those landscapes move. Researchers have noted unusual migration patterns in some species in recent years. Whether the magnetic changes are responsible is still being investigated, but the timing aligns. The tug-of-war over the north is also tied to what is happening in the south. Some models suggest that as field strength shifts in one hemisphere, compensating changes appear in the other. The reorganization of the global field is a connected phenomenon, not a series of isolated events. The South Atlantic anomaly, the drifting North Pole, the shrinking Canadian zone, the growing Siberian zone, these are all part of the same deep rearrangement. The planet is rebalancing its magnetic structure, slowly, across decades, with visible results showing up in compasses, satellites and bird migrations, and every once in a while, the deep dynamics break through to the surface in dramatic fashion. In September 2005, the Afar Desert in northeastern Ethiopia opened up. For about 10 days, a swarm of earthquakes rattled the region. Then the ground started moving in ways no one had ever seen at that scale. Cracks appeared, they widened, they connected. By the time the activity quieted, a fissure 35 miles long had ripped across the desert. In some places, the gap was up to 25 feet wide. The 2 sides of the fissure had separated by as much as 8 meters. About 26 feet. What had happened? A massive injection of magma from below had forced its way into the crust. Geologists call this a dike intrusion. A vertical sheet of molten rock pushed up through cracks in the rock, prying the crust apart from the inside. As it spread, the surface above split along its length. The Afar event was studied immediately. International teams flew to Ethiopia. Sensors were deployed. The data revealed that the dike was about 35 miles long, between 2 and 9 miles deep, and contained an estimated 2.5 cubic kilometers of magma. The amount of new magma injected in those days was roughly equal to the volume of one of the larger volcanic eruptions in recent history, except this magma did not erupt. It mostly stayed in the crust, prying it apart. The Afar event was the largest documented continental rifting episode in modern times. It demonstrated that rifting does not always happen at the slow, smooth pace that satellite measurements suggest. Sometimes the planet stores up strain for decades, then releases it in a burst. A few millimeters per year of average drift can be punctuated by a single 10-day event that adds 8 meters in one place. It was, in other words, an earthquake's first cousin. Not a sudden release of stored mechanical strain along a fault, but a sudden release of stored thermal pressure through a sheet of magma. Picture squeezing a tube of toothpaste with a small crack in the side. For weeks, nothing happens. Then, all at once, a long, thin streak of paste shoots out along the crack. The toothpaste finds the easiest path and uses it explosively. The Afar decay was the planet doing the same thing with rock and fire. What does this teach us about the East African rift? It tells us that the rift is not just slowly stretching, it is loading. Strain accumulates in the crust until something gives. When something gives, it can give in a hurry. The 4 to 7 millimeter per year average is a long-term smoothing of dramatic episodic events. It also tells us that the next big rifting event in East Africa is not a question of if, but when. Geologists watching the Afar region have detected several smaller dike intrusions since 2005. Some have caused volcanic activity. Some have lifted and dropped portions of the surface by tens of centimeters. The system is alive and active. In November 2025, a volcano in the Afar region named Haley Gubby erupted for the first time in recorded history. Volcanoes do not normally do that. When a previously silent system suddenly comes online, it is a sign that the underlying magma supply has changed. Something is moving down there. New pulses of mantle material are reaching new corners of the rift. The pace of African rifting is no longer a story of patient millimeters. It is a story of patient millimeters punctuated by violent days. And while the African crust prepares for its next surge, beneath California a different kind of seismic story is unfolding very quietly. In January 2026, a study published in Science Daily revealed something surprising about California. Beneath the northern part of the state, scientists had been watching swarms of tiny earthquakes far too weak to be felt. Hundreds of them. Maybe thousands. They had been going on for years without anyone fully appreciating what they meant. When the team mapped the swarms in detail, they realized they had stumbled onto a hidden and surprisingly complex earthquake zone. These were not the famous big quakes California is known for. They were microquakes, magnitudes less than 2, sometimes less than 1. Each one would not even rattle a coffee cup. But, added together, they painted a picture of an entire fault system that had been working in secret. The faults were small. They were short. They were tucked into rock layers that traditional seismic networks had trouble resolving. Why did this matter? Because microquakes are not just noise, they are pressure relief valves. When stress builds in the crust, some of it is released through small slips along small faults. By tracking when and where the microquakes happen, scientists can map the strain field of an entire region. The patterns reveal which sections of larger faults are sliding smoothly, which are locked, and which are about to give. Until recently, microquake data was hard to collect outside of areas with dense seismic networks. Northern California has decent coverage, but not great. The recent advance came from machine learning. Algorithms trained on enormous databases of seismic waveforms can now pull tiny quakes out of background noise that humans would have dismissed. The result has been a sudden flood of new data. The hidden zone the algorithms revealed sits beneath a region that was thought to be relatively quiet. Instead, it is alive with microscopic activity. The activity clusters along faults that had not been mapped at full detail before. Some of those faults connect to larger systems further south. What are the implications? The first is that strain is being released in places where geologists did not expect it. That is good news in some ways. Strain that releases in tiny quakes is strain that is not stored up for a big one. But it is also bad news because it suggests that the underlying fault networks are more interconnected than the older models showed. A rupture on one fault could trigger neighbouring faults that nobody had on their hazard maps. The second is that California's seismic story is not limited to the San Andreas system. The hidden zone is part of a wider, more diffuse pattern of strain release that stretches across the entire western United States. Similar hidden zones are likely sitting under other states. Some have already been proposed for parts of Nevada, Oregon, and Utah. The third is that machine learning is changing seismology. The same techniques that revealed the Northern California zone are being applied to seismic records globally. New microquake catalogues are appearing every few months. Each one adds more detail to a picture of the planet's surface as a constantly buzzing crystal lattice, slipping in millions of tiny ways every year. Picture a glass window under stress. To the eye, it looks solid and intact. Under a microscope, you would see thousands of microcracks slowly forming and propagating. Each one is invisible. Together, they tell you the window is straining and might one day shatter. That is California, viewed at the resolution our new tools allow. But the strangest seismic phenomenon of all does not crack a glass window in seconds. It cracks one over months. Most earthquakes are over in seconds. The biggest, like the Kamchatka 8.8, last about a minute. After that, the ground is still and the aftershocks begin. That is the model of an earthquake everyone grows up with. But there is another kind of quake that breaks every rule of that model. They are called slow-slip earthquakes. They release the same kind of energy as regular quakes. They involve the same kind of fault motion. But instead of finishing in seconds, they take days, weeks, or months, sometimes more than a year. You cannot feel a slow-slip earthquake. The ground moves so gradually that no human nervous system would register the motion. A magnitude 6 slow-slip event might unfold over half a year, with the crust sliding a few centimetres during that entire period. A regular magnitude 6 quake would slide a comparable distance in seconds. The first slow-slip earthquakes were detected in 2001, almost by accident. Scientists studying GPS data from Japan and the Pacific Northwest noticed that some monitoring stations were drifting in ways that made no sense. The drift was too slow to be a quake, too fast to be normal tectonic motion, and it would last for a few weeks before stopping. It turned out the GPS stations were riding a slow-slip event. The fault below was moving. The energy was the same as a regular earthquake, but the speed was 1,000 times slower. Slow-slip events have since been found at subduction zones around the world. Cascadia has them every 14 months or so, like clockwork. Japan has them in different patterns. New Zealand has them. They tend to happen in the deep parts of subduction zones, just below where the fault is locked. They quietly release strain that would otherwise build up further. But slow-slip events are also troubling. Some of them happen right next to locked sections of major faults. When a slow-slip event begins, the slipping section starts loading the locked section nearby. The locked section feels a sudden push. If it was already close to its breaking point, the push could trigger a real earthquake. A large one. Some seismologists believe that several historic megathrust earthquakes were preceded by slow-slip events that nobody at the time could detect. The Tohoku quake in 2011, which caused the Fukushima disaster, was apparently preceded by a slow-slip event in the months and weeks before. Scientists who looked back at GPS data after the fact found a clear signal that nobody had noticed in real time. That is what makes slow-slip events both useful and dangerous. They are useful because they release strain harmlessly most of the time. They are dangerous because they can sometimes nudge a locked fault into a sudden, devastating rupture. Picture a heavy door that has been wedged shut for years. The wedge is barely holding. Then someone leans against the door, gently, for hours. Most of the time, the door does not open. The pressure dissipates through the wedge. But every once in a while, the steady push is just enough to pop the wedge out, and the door slams open all at once. Slow-slip events are the gentle leaning. Megathrust earthquakes are the door slamming open. The latest research suggests that slow slip events are far more common than anyone realized. Newer GPS networks and machine learning algorithms are detecting hundreds of small ones per year. Some last hours. Some last days. The picture emerging is of a planet whose subduction zones are constantly shedding strain in fits and starts, with the occasional violent release thrown in. But not every strange phenomenon happens at faults. Some happen inside the deepest, densest part of the planet. The inner core is doing things that, until recently, scientists did not believe were physically possible. Until very recently, the inner core was supposed to be simple, a solid sphere of iron and nickel, packed under enormous pressure, behaving like a giant, perfectly crystalline metal ball. In December 2025, that picture got complicated by a new study suggesting Earth's solid inner core might actually be in something called a superionic state. Not solid the way ice is solid, not liquid the way water is liquid, something in between. Something that breaks the usual rules of how matter behaves. A superonic material is a strange beast. It has a rigid framework of heavy atoms locked in place like a crystal. But threaded through that framework, lighter atoms move freely, almost like a liquid. The heavy atoms hold their positions. The light atoms flow between them. The whole material is technically solid, yet it conducts electricity like a liquid metal and allows certain chemicals to migrate through it as if it were a sponge. Superonic states have been observed in laboratory experiments at pressures and temperatures similar to those inside Earth's core. The studies suggest that under those conditions, hydrogen, oxygen, and possibly other light elements dissolved in iron could behave as a flowing internal sea inside an otherwise solid metal sphere. If the inner core is superonic, that changes everything. It changes how heat escapes the inner core, because superonic materials conduct heat differently. It changes how the inner core's surface deforms, because light elements can rearrange themselves in response to forces from above. It changes how the magnetic field is generated, because moving charges inside the inner core can interact with the outer core's currents in new ways. It also explains some of the recent observations that seemed otherwise impossible. The shape changes Vidal's team detected, the seismic anomalies at the inner core's surface, the unexpected heat flow rates. All of these become easier to understand if the inner core is not a static sphere, but a partly fluid matrix where light elements are migrating internally. Picture a chunk of Swiss cheese with water inside the holes. The cheese is solid, the water is liquid. From the outside, the cheese keeps its shape, but the water inside can slosh around, change distribution, and even leak slowly through the cheese walls. That is roughly how a superonic inner core would behave, except instead of cheese and water, it would be iron and hydrogen. The implications go further. Some researchers now suggest that the inner core might be slowly losing certain light elements to the outer core, much like a sponge slowly leaking water. Over geological time, that loss would change the composition of both layers. The outer core would gain light elements, the inner core would solidify further, and the interaction between the two would generate stronger currents and more dramatic magnetic disturbances. The superonic hypothesis is still being tested. Direct evidence is impossible to gather, since no probe can reach the inner core. But laboratory experiments at extreme conditions, combined with seismic observations and computer simulations, are converging on a picture that increasingly favours the idea. If it turns out to be right, then the deepest, densest part of Earth is not a simple solid ball, it is something stranger. A crystal full of moving fluid, a matrix that is solid and liquid at the same time, depending on how you look at it. And inside that matrix, heavy elements that used to be considered locked in place might not be locked in place at all. Some of them might be slowly creeping toward the surface. In May 2025, a study made waves in geochemistry circles. Researchers analysing volcanic rocks from Hawaii had found unusual ratios of certain heavy metals. The ratios suggested that small amounts of those metals had originated not in the mantle, but in the outer core. They had migrated upward from the core into the mantle, and then risen in plumes to the surface, where they had erupted as part of Hawaiian lava. Among the metals showing this signature was gold. This was a big deal. For most of the history of geology, the core was considered a closed vault. When the planet was forming, dense metals like iron, nickel, and most of Earth's gold had sunk to the centre. Once they were down there, they were assumed to stay down there. The mantle and crust were left to make do with the small fraction of heavy metals that stayed in the upper layers. The new findings suggested otherwise. Some of that core gold has been leaking out. The mechanism is not yet fully understood, but it appears that material at the core-mantle boundary, where the molten outer core meets the bottom of the mantle, can chemically interact in ways that allow tiny amounts of gold and other heavy elements to enter the mantle rock. From there, mantle plumes pick up the elements and carry them upward. Over millions of years, the plumes erupt at hotspots like Hawaii, depositing the elements into volcanic rock. The amounts are small. We are not about to mine the bottom of the mantle. But the discovery has profound implications for how the planet works. It means the core is not a closed system. The mantle and core are exchanging material slowly and continuously through chemical reactions and convection at their shared boundary. Heavy elements that have been locked up since planet formation are gradually rejoining the geochemical cycles of the upper Earth. It also means our understanding of where gold and other valuable elements come from is incomplete. Some of the gold mined on the surface might trace its lineage back to the core, having taken billions of years to make its way upward through plumes and eruptions. Geochemists are now reanalyzing classic gold deposits, looking for the same signature. There is a deeper question lurking behind the gold story. If heavy elements are migrating from the core to the mantle, what else might be migrating? Some researchers suspect that other elements, including platinum, ruthenium, and certain isotopes, are taking the same journey. Each element leaves a different signature in the rocks above. By tracing those signatures, geochemists hope to map the chemical exchanges happening at the core-mantle boundary in detail. The boundary itself is not flat. It has hills and valleys, sometimes called core topography. The hills can poke up into the mantle, the valleys can sink into the outer core. Each feature might be a site of different chemical exchange. The picture emerging is of a boundary that is busy, constantly trading heat, chemicals, and pressure between the two largest layers of the planet. Picture the bottom of an old kettle that has been used to boil water for years. A thin layer of mineral deposits forms where the water meets the metal. Some material from the water gets locked into the kettle. Some material from the kettle gets into the water. The boundary is a chemical zone, not just a wall. The core-mantle boundary is the same idea, scaled up to 2,000 miles deep. And on that boundary, where chemistry is exchanged and heat escapes, there are two enormous structures that no one had any idea existed until recent years. They are roughly the size of continents. And they have been hiding in plain sight, 2,000 miles below the surface, sitting on the boundary between the mantle and the outer core. There are two structures that geologists never expected to find. They are massive. They are dense. They are roughly the size of continents, and they appear to be far older and more stable than almost anything else inside the planet. Geologists call them large low shear velocity provinces, or LLSVPs. The name is a mouthful. It refers to the fact that seismic shear waves slow down dramatically when they pass through these regions. The waves are essentially being absorbed and scattered, the way light is absorbed by smoke. There are two of these structures. One sits beneath the African continent, the other sits beneath the Pacific Ocean. They are roughly antipodal, which means they are on opposite sides of the planet from each other. Each one is about as wide as a continent. Each one is about 1,000 kilometers tall. In January 2025, a study described these regions as subterranean islands and pointed out that they are not only hotter than the surrounding mantle, but also potentially less turbulent. They are thought to be made of denser, chemically distinct material that is somehow resistant to mixing with the rest of the mantle. What are they? The honest answer is that nobody fully knows. There are several leading hypotheses. One idea is that they are graveyards of ancient subducted ocean crust. Over hundreds of millions of years, slabs of cold, dense ocean floor have plunged into the mantle and accumulated near the core boundary. The accumulated material, denser than the surrounding mantle, settled into stable mounds. The two LLSVPs would then be giant piles of recycled ocean crust. Another idea is more dramatic. Some researchers think the African and Pacific LLSVPs are remnants of a giant impact early in Earth's history. The same impact that created the Moon. According to this hypothesis, parts of the impactor, called Theia, sank into the early Earth's mantle and never fully mixed. They settled at the base of the mantle and have been sitting there for over 4 billion years. The two LLSVPs would then be alien material, frozen in place beneath the crust. A third idea is that the LLSVPs are simply hotter, chemically primitive mantle that has resisted convection because of its different density. They would be ancient material that survived the planet's mixing, isolated by their own physical properties. Whatever they are, they have huge effects on the surface. The LLSVPs sit directly under hotspots. The Pacific LSVP underlies the Hawaiian and Polynesian volcanic chains. The African LSVP underlies the East African Rift, the Afar Plume, and parts of the Atlantic hotspots. These are not coincidences. The LLSVPs appear to be the source regions for many of the planet's deepest mantle plumes. The Afar heartbeat, the one that is splitting Africa, almost certainly originates from material rising off the African LSVP. That means the breakup of Africa is being driven by an island of strange, dense rock that has been sitting beneath the continent since long before there were continents in the modern sense. It also means that the LLSVPs may be partly responsible for the magnetic field changes happening above them. The South Atlantic anomaly is positioned roughly above the western edge of the African LSVP. If the LSVP is influencing how heat escapes the core in that region, it could be shaping the patterns of reversed flux drifting beneath southern Africa. Picture two enormous undersea mountains, each the size of a continent, sitting on the boundary between the mantle and the core. Heat has to flow around them, currents have to bend around them, plumes rise off their edges. They are the deep Earth equivalent of weather-shaping land masses, except they have been there for billions of years, and they are made of something we still cannot identify. And out of those structures, gas is constantly being pushed upward through the rest of the planet. Stand near a geyser at Yellowstone, and you can sometimes smell sulfur on the wind. That smell is the planet exhaling. It is gas that has travelled hundreds of miles from deep inside Earth, up through cracks in the rock, and into the air you breathe. The chemistry of these emissions tells a story. For decades, geologists have been measuring the carbon dioxide that rises from volcanic and geothermal regions. The numbers were always larger than expected. Yellowstone alone emits about 40,000 to 50,000 tons of carbon dioxide per day. Multiply that by every active volcanic region on Earth, and you get a planetary CO2 budget that is significantly more than what shallow magma chambers can produce. The discrepancy was a puzzle. Where was the extra gas coming from? The discovery of the deeper Yellowstone reservoir, 12 to 28 miles below the surface, helped solve part of the puzzle. The lower reservoir is much larger and emits gas in addition to the upper chamber. But even that does not fully account for all the carbon dioxide rising from volcanic regions worldwide. Some of the gas appears to be coming from much deeper, from the boundary between the mantle and the outer core, from the LLSVPs, from the slow chemical exchanges happening at the core itself. This is a relatively new realization. The idea that Earth's core is contributing gas to the surface, on timescales we can measure, would have been considered fringe a few decades ago. Today it is mainstream geochemistry. The signatures of certain gases, especially helium-3 and certain noble gas isotopes, can be traced back to material that has been sitting near the core for billions of years. When you find those signatures coming out of a volcano, you know that volcano is connected to the deepest layers of the planet. Hawaii is one of the strongest sources. Iceland is another. The Afar plume is a third. Each of these is fed by a deep mantle plume that rises from near the core boundary, picking up ancient gas as it goes. The gas matters for a few reasons. First, it tells us that the planet is leaking. Slowly, continuously, not just heat. Gas. Material from the deepest interior is making its way to the atmosphere. Over geological time, that means the inventory of light elements inside the deep Earth is gradually decreasing. Second, the rate of leaking might be changing. Some recent studies suggest that the carbon dioxide flux from certain volcanic regions has crept up over the last few decades. The increases are small, but they are measurable, and they correlate with the same period in which the core has been showing other signs of unusual behaviour. Third, the gas affects the climate. Volcanic CO2 is a small fraction of total atmospheric CO2 compared to human emissions, but it is not negligible. If the volcanic flux is rising, even slightly, it adds to the long-term thermal trajectory of the planet's surface. Picture an old steam engine slowly venting through small cracks in its boiler. The vents are small. The steam is dispersed. But if you watched for centuries, you could measure the amount of steam released and learn something about the engine's internal pressure. The volcanic and geothermal gas emissions of Earth are exactly that. They are the readouts of a deep, hot engine, and they are telling us the engine is running steadily, with maybe a slight uptick in some places. And that engine, with all of its leaking gas and shifting flux patches and migrating heavy elements, might be subtly changing how fast the planet itself is spinning. A day is supposed to be 24 hours, 86,400 seconds, steady, predictable, the basic clock by which all of human civilization runs. It is not. Earth's rotation rate fluctuates, constantly. Most of the variations are tiny, less than a millisecond per day. They come from atmospheric movements, ocean tides, redistribution of mass on the surface from melting ice, and the deep dynamics of the core. But they are real. They are measured every day by atomic clocks linked to GPS satellites and very long baseline interferometry, which uses radio signals from distant quasars to track the planets. Orientation in space. In recent years, those measurements have shown something puzzling. The planet has been slightly speeding up. Days have been getting marginally shorter. In 2020, Earth recorded its shortest days since direct atomic measurements began in the 1960s. The shortening continued through 2021, 2022, 2023, and 2024. By 2025, several individual days had clocked in roughly 1.5 milliseconds shorter than the standard. The cumulative effect has been enough to put atomic timekeepers in a strange position. For the first time in history, the world's official timekeepers are seriously discussing the possibility of subtracting a leap second instead of adding one. A negative leap second has never happened. The leap second system was designed in 1972 to add seconds to clocks, accommodating a slowly slowing planet. Now the planet has reversed course, and the system might have to subtract a second to keep atomic time aligned with astronomical time. What is causing the speed up? A combination of factors. Climate change is moving mass around. As ice melts at the poles and water redistributes, the planet's moment of inertia changes, and its rotation rate adjusts accordingly. Earthquakes can also shift mass and change rotation, though usually only by microseconds. But a major factor is the inner core. Fidel's team noted that the slowdown of inner core rotation, the very phenomenon at the heart of so many other changes, can affect the length of a day. When the inner core slows relative to the surface, the angular momentum has to go somewhere. By conservation of angular momentum, the rest of the planet has to compensate. The mantle and crust speed up by tiny amounts. The effect is small, 1,000th of a second per day, almost lost in the noise. but it is exactly consistent with the timing of the inner core changes. The slowdown began around 2010. The day shortening accelerated through 2020. Picture an ice skater pulling her arms in to spin faster. Her body has the same energy as before, but the mass is closer to her axis. So the rotation speeds up. Earth has been doing the same thing in reverse, with the mass being subtly redistributed by changes deep inside. There is no danger from any of this. Days will continue to be roughly 24 hours long for as far as anyone can practically plan. But it is another reminder that the planet's basic parameters are not fixed. The clock by which we measure all of human time is running on a slightly variable engine. It is one more line in the data. One more piece of evidence that the deep Earth is changing. And one more reason to ask what changes might be coming and how soon some of them might break through to the surface in a way humans cannot ignore. Because some of those changes will not take millions of years. Some of them might happen on timescales that matter to us. Here is a slow-motion catastrophe that is not actually a catastrophe. It is a birth. The East African Rift is not just splitting Africa. It is creating an ocean. The same process that opened the Atlantic 200 million years ago, that created the Red Sea 20 million years ago, that built the modern Indian Ocean, is now playing out in real time across Ethiopia, Kenya, Tanzania, and Mozambique. In the most distant projections, scientists believe that within 5 to 10 million years, the Indian Ocean will pour into the Rift Valley. The breach will probably happen first at the northern end, in the Afar Triangle, where the crust is thinnest and the magma supply is most active. Salt water will flood in. Coastlines will form on what is now desert. Over the next 10 to 30 million years, the inflow will deepen. The new ocean will expand. The eastern part of Africa, including most of Somalia, parts of Ethiopia, eastern Kenya, eastern Tanzania, and Madagascar, will drift away from the rest of the continent. A new sea, possibly hundreds of miles wide at first, will separate them. By 50 million years, the new ocean could be comparable to the Red Sea today. By 100 million years, it could rival the size of a young Atlantic. By 200 million years, the eastern fragment might have become a small continent of its own, drifting across the Indian Ocean toward Asia. This is not science fiction. It is the standard playbook of plate tectonics, repeated dozens of times over the history of the planet. What does it mean for human time? Almost nothing in the next few thousand generations. The rift moves at fingernail speed, the volcanoes erupt now and then, the earthquakes shake, but the actual ocean will not arrive within any timescale that current human civilization plans for. But the effects are visible already. Land in the rift is sinking and rising. Lakes are forming and draining as the surface deforms. Volcanoes are reactivating. The Haley Gubby eruption in 2025 was one of several recent surprises. Mount Nyiragongo in the Democratic Republic of the Congo continues to maintain a lava lake. Oldoinio Lengai in Tanzania erupts a strange mineral-rich black lava unique on the planet. Local effects matter for the people living in the region. Earthquakes in the rift can be devastating. Volcanic activity threatens cities and farmland. Geothermal energy, however, has become a major resource. Kenya's Olkaria geothermal complex, sitting squarely inside the rift, is one of the largest geothermal power installations in Africa. The same forces that will eventually destroy the current geography are powering homes today. The rift also affects climate. Lakes that form in the rift influence regional weather patterns. The mountains that rise along the rift valleys block winds and shape rainfall. The Congo Basin rainforest, the second largest in the world, depends partly on the way the rift redirects atmospheric flows. Picture pulling on a piece of warm taffy. Slowly, but with perfect persistence. The taffy stretches. The middle thins. Eventually a new piece pinches off. Africa is being pinched off, fingernail by fingernail, with a very specific point on the planet sliding away from the rest. It is the most dramatic geological process happening on land anywhere on Earth right now. And while Africa is being slowly born into a new shape, the Pacific Northwest is staring down a much shorter timeline. The Cascadia subduction zone runs from northern California up to British Columbia, about 700 miles long. For most of that length it has been locked. Strain has been building since its last major rupture in 1700. Geologists know about that rupture from sediment cores, tsunami deposits in coastal lakes, and Japanese tsunami records that match the date. The 1700 rupture was about a magnitude 9. It dropped large parts of the Pacific Northwest coastline by several feet. It generated a tsunami that crossed the Pacific Ocean and hit Japan 10 hours later, carving its place into Japanese historical records. It left ghost forests, stands of cedar trees killed by sudden saltwater inundation that still mark the coast today. Cascadia ruptures of that size are estimated to happen every 200 to 600 years on average. The 1700 quake was over 300 years ago. The system is loaded. Now, the new findings about Cascadia's slab tearing add a wrinkle. The basic picture is that Cascadia is dying as a subduction zone. The slab is fracturing, microplates are forming, new slab windows are opening. But this dying process is happening over millions of years. In the immediate term, the locked main section of the fault, the part that produces the magnitude 9 quakes, is still locked. Still loading, still capable of producing the same kind of catastrophe it produced in 1700. What the new tier discoveries change is the complexity of the rupture, if it happens. The Louisiana State University team is investigating whether a major earthquake could rupture across one of the new slab tears. If it did, the rupture might propagate in unexpected directions. Energy might travel along the tiers as well as along the main locked section. Ground motion patterns at the surface could be more uneven than current models predict. Some areas might shake harder than expected, others might shake less. This is the kind of detail that matters to building codes, evacuation plans, and tsunami warning systems. A Cascadia magnitude 9 event today would be one of the most expensive natural disasters in US history. Estimates from recent FEMA modelling suggest tens of thousands of casualties, hundreds of billions of dollars in damage, and decades of recovery for the Pacific Northwest. Tsunamis would hit coastal communities within 15 to 30 minutes of the rupture, often less. Many coastal towns would have to evacuate immediately, on foot, with no time for cars. The probability of a magnitude 9 on Cascadia within the next 50 years is estimated at about 10%. The probability within the next 100 years is around 30%. Within 300 years, it approaches near certainty, given the 1700 precedent. Picture a heavily loaded spring. It has been compressed for 3 centuries. You cannot see how compressed it is. You cannot tell exactly when it will release. But you know that springs do not stay compressed forever. Eventually, the energy stored has to come out. And when it does, it will come out fast. The slab tiers mean the spring is sitting in a more complicated cradle than scientists used to think. The release might not be a single clean snap. It might involve several connected releases. The tier-induced complexity adds uncertainty in both directions. What is certain is that the deep Earth's behaviour is feeding into surface hazards in new and interconnected ways. The mantle is restless, slabs are tearing, subduction zones are dying, and the seafloors of the world are beginning to look as dynamic as the continents above them. But there is one more deep secret about subducted slabs that turns the whole picture stranger. When ocean plates subduct, they sink into the mantle. Eventually, they reach the core-mantle boundary. There, the slabs accumulate. They pile up. They compress. They are crushed against one of the densest interfaces inside the planet, and there they sit. This is the slab graveyard. It is a layer of compressed ancient ocean crust that has been collecting at the bottom of the mantle for hundreds of millions of years, possibly billions. The April 2026 study from Wolf and the team that mapped deep mantle deformation found that the graveyard is huge. Most of the seismic anisotropy in the deepest mantle the directional patterns in seismic waves comes from regions where slabs are believed to have piled up. The graveyard's footprint covers significant portions of the core-mantle boundary. What is happening in the graveyard? A few things, all unsettling. First, the slabs are still warm enough to be slightly less dense than the dense lower mantle around them. Some of them might be thermally rebounding upward, very slowly, after their long descent. The graveyard is not entirely a graveyard. Some of the slabs are starting their journey back up, fueling the next generation of mantle plumes. Second, the slabs are chemically interacting with the core boundary. They contain sediment, water, oxidized minerals, and minor amounts of organic material that started as living things on the ancient ocean floor. As they crush against the core boundary, those materials react with the iron in the outer core. The reactions release new chemicals. Some of those chemicals seem to migrate upward. Gold from the core might be only one example of how the boundary chemistry feeds the mantle above. Third, the slabs influence the magnetic field. Their cold, dense material affects how heat flows from the core. Where the slabs sit, the core surface cools differently. The cooling pattern shapes the convection currents in the outer core. The convection currents determine the magnetic field. So in a very real sense, the position of ancient slab debris is helping to draw the magnetic map of the planet today. The reversed flux patches under Africa, the ones drifting and merging beneath the South Atlantic anomaly, are positioned over a region where significant slab material is thought to have piled up over the last few 100 million years. The cool spots in the mantle there are influencing the field above. The South Atlantic anomaly, in other words, might be a surface reading of an ancient slab graveyard. Picture a beach at low tide. Stones, shells, and bones of ancient sea creatures are scattered across the sand, embedded over centuries. As the tide comes back in, currents flow around those stones in specific patterns. The water swirls one way around large stones, another way around smaller ones. Anyone watching the water alone would see a complex pattern. Only by knowing the stones underneath could you predict the swirls. That is the deep mantle. The slabs are the stones. The convection in the outer core is the water. The magnetic field at the surface is the swirl pattern. The connections run all the way from prehistoric ocean floors to the GPS in your phone. The graveyard is also adding to itself. New slabs are subducting now. The Pacific plate is sinking. The Cascadia plate is fracturing on its way down. Each of these contributions joins the older graveyard, building it slowly, decade by decade. In 10 million years, the graveyard will be slightly larger and slightly differently shaped. The magnetic field patterns above it will respond. Convection currents will adjust. A future South Atlantic anomaly equivalent might form somewhere completely different, depending on where the new slab debris settles. And all of this raises the most dramatic question hanging over geomagnetic science. Could the magnetic field in the next several thousand years do something it has done many times before? Could it flip? Throughout Earth's history, the magnetic field has reversed itself. North becomes south. South becomes north. The flip happens every 200,000 to 1 million years on average, and the geological record preserves the evidence in volcanic rocks. When magma cools and solidifies, the iron in it locks onto the direction of the magnetic field at that moment. By drilling into ancient lava flows, scientists can read the magnetic history of the planet going back hundreds of millions of years. The reversals are recorded clearly. The most recent full reversal happened about 780,000 years ago in an event called the Brunhers-Matuyama reversal. We are statistically overdue for another one. A flip is not a sudden event. It takes thousands of years to complete. During the transition, the magnetic field weakens significantly. Sometimes it nearly disappears in some regions, while strengthening in others. Multiple weak poles can exist temporarily. Then, eventually, the field reorganizes around a new orientation, and the dipole reasserts itself in the opposite direction. The South Atlantic anomaly has caught the attention of researchers studying flips. It looks suspiciously like the early stage of one. a growing weak spot, reversed flux patches drifting and merging beneath it. Asymmetric weakening across hemispheres, faster decline in recent decades. All of these features have been seen, in some form, at the start of past reversals. Are we headed for a flip? The honest answer is that nobody knows. Some studies, looking at patterns of past behaviour, suggest the current changes might be the early signs of a transition that could play out over the next 1 to several thousand years. Other studies note that the field has weakened and recovered many times without flipping. About 80% of the time, weak periods stabilise and the field strengthens again. Only about 20% end in a full reversal. The current data does not allow a definite prediction. The South Atlantic anomaly might keep growing for centuries and then stabilise. It might split into multiple weak zones that eventually merge into a transitional state. It might collapse the dipole entirely. We will not know which path Earth is on until much more time has passed. What would happen if a flip did happen? The most cataclysmic predictions are not supported by evidence. Past flips do not appear to have caused mass extinctions. Life on Earth has gone through many of them without obvious harm. The atmosphere remained largely intact. Animals adapted, ecosystems continued. But modern civilization is a different story. A weakened magnetic field during a flip would expose satellites to far more radiation. GPS, communications, and weather satellites would face significantly higher failure rates. Astronauts could not safely conduct long-duration missions in the affected regions. Power grids, especially long-distance transmission lines, would be more vulnerable to solar storms which the field normally deflects. Animal navigation would be disrupted. Migratory birds, sea turtles, and certain fish use the magnetic field to guide their journeys. A reorganizing field would scramble their ancestral maps. Over generations, species would adapt, but the transition could be hard on populations. Aurora patterns would change. Right now, the auroras are largely confined to the polar regions. During a flip with multiple weak poles, the auroras could spread to lower latitudes. People in the tropics might see them for the first time in human history. The probability that a flip is starting now is not negligible, but it is also not high. Scientists watching the data are cautious. The field is doing things it has not done in the modern era of measurement, but those things are still well within the range of normal variability. A flip is possible. A flip in the next millennium or two is possible. A flip in the next century is not the most likely scenario, based on what we know. But the data being collected now by the swarm satellites and their successors is the most detailed record of geomagnetic behaviour ever assembled. Whatever the field does next, this generation of scientists will see it coming with more clarity than anyone before. And that brings us finally to the verdict on everything we have looked at. Step back from the details for a moment. Here is what we have learned. The inner core is rotating differently than it has in living memory. Its surface is changing shape. Its interior may be partly fluid in ways no textbook captured until recently. Light elements may be migrating through it. Gold may be rising from it. The angular momentum it sheds is making days slightly shorter. The outer core is more dynamic than the textbook suggested. Reversed flux patches are drifting and merging beneath the southern hemisphere. The South Atlantic anomaly is growing. The magnetic North Pole is racing across the Arctic. Geomagnetic jerks are coming more often. Strong field zones are migrating. The deepest mantle is hosting solid-state convection, with crystals aligning in ways that race seismic waves. Continent-sized islands of strange, dense rock are sitting on the core boundary, shaping plumes and possibly the magnetic field above. Ancient subducted slabs are piling up there, leaking chemicals and influencing heat flow. The mid-mantle is producing earthquakes that were not supposed to exist. The crust is fragmenting in places like Cascadia. Subduction zones are dying. New microplates are being born. At the surface, Africa is splitting in two. The Pacific Northwest is preparing for a major rupture, Yellowstone is breathing through a leaky lid. Hidden zones of microquakes are mapping new fault networks every year. Slow slip events are quietly redistributing strain. Earth is exhaling gas from its deepest layers, and the planet itself is cooling faster than the textbooks said. What does it all add up to? 3 things, with 3 different levels of certainty. First, there is no doubt that something significant is happening inside Earth right now. The signals are real, the data is solid, they are being recorded by satellites, by seismometers, by GPS networks, by atomic clocks, by laboratory experiments. The picture they paint is consistent. The interior of the planet is reorganizing on a scale we have never measured before. Second, the changes are happening on multiple timescales. Some, like the inner core slowdown and the magnetic field weakening, play out over decades. Some, like the splitting of Africa, take millions of years. Some, like the next Cascadia megaquake, could happen at any moment within the next few centuries. Connecting them is the recognition that the planet is one system, with the deep interior shaping the surface in ways we are only just beginning to map. Third, none of this is reason for panic. The planet has been through many such reorganizations. Life has survived all of them. Civilizations will survive these. The dramatic changes that capture headlines play out on time scales most humans cannot perceive. Even the dramatic short-term events like a major earthquake are statistically rare and increasingly well prepared for. But the picture has changed. We used to think of Earth as a settled place. Tectonic plates moving slowly, magnetic field steady, core boring, mantle quiet. Modern science has dismantled that picture in less than a decade. The planet is not settled, it is dynamic. Every layer, from the inner core to the atmosphere, is exchanging energy and matter with every other layer in ways that are interconnected and changing. The implication for science is enormous. The implication for our species is more philosophical. Humans have always lived with the assumption that the ground beneath our feet is reliable. It is, on the scale of a human life. But over decades and centuries, things shift. Compasses drift. Continents inch apart. Volcanoes wake up. Earthquakes rip open the surface. The planet is alive in a sense. It has rhythms. It has cycles. It has surprises. The decade we are living in now happens to be one of the most informative decades in the history of geophysics. New satellites, new computers, new algorithms, new experiments. We are seeing the deep Earth more clearly than any generation before us. The picture is more strange and more dynamic than anyone anticipated. What comes next? More data, more surprises, probably more changes. The planet does not stop. It keeps running its slow, immense engines, and we keep listening. Hold on, because the next decade of measurements will tell us things that no human has ever known, about a planet that is far more alive than its silent blue surface suggests.